One of the important parts of algebra is the binomial theorem. Now, a plus b has two terms, a and b. That's why it's a binomial. We can raise it to different powers. Well, a plus b to the 0 gives us 1. A plus b to the 1 gives us 1a plus 1b. Now, if we have the index here as 2, we're going to have to do a plus b times a plus b, which involves FOIL, which gives us this expression, 1a squared plus 2ab plus b squared. If we raise this binomial to the third power, we get 1a cubed plus 3a squared b plus 3ab squared plus 1b cubed. A plus b to the fourth, this binomial to the fourth power, gives us 1a to the fourth plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the fourth. Now, let's look for some patterns, because this could continue on for a long time. We're going 1, then 1, 1. If we add 1 and 1, we get 2. If we add 1 and 2, we get 3. And 1 and 2, we get 3. We have 1s on the outside always. 1 and 3 gives us 4. 3 and 3 gives us 6. 3 plus 1 gives us 4. And we have 1 on the outside. Let's look at what's happening to the a term, or the first term. It goes a to the 1, then a squared, a to the 1, a to the 0. A cubed, a squared, a to the 1, a to the 0, a to the fourth, a to the third, a squared, a to the 1, a to the 0. Let's look what happens to the b term. Here we have b to the 0, b to the 1, b squared. B to the 0, b1, b squared, b cubed. B to the 0, b1, b squared, b cubed, b to the fourth. Also, you can see that the exponents add up to whatever your index is here. So a squared gives us 2. A to the 1 plus 1 gives us 2. B squared gives us 2. A cubed gives us 2. A to the 2 plus 1 gives us 3. 1 plus 2 gives us 3. Here with the fourth power we have a cubed, b1 gives us 4. Squared and squared gives us 4. 3 and 1 gives us 4. And of course 4 and 0 gives us 4. So there's lots of patterns as we expand a binomial. We are going to get to the binomial theorem, but let's talk about Pascal's triangle first. If I'm trying to expand this binomial, a plus b to the n, I can consider the coefficients, and Pascal's triangle will give me those coefficients. What's important to note here always is that we're starting with n equals 0 because a plus b to the 0 gives us 1. When the exponent here is 1, then we get coefficients on a and b of 1 and 1. 1, 1 is 2, so it gives us 1, 2, 1. 1 and 2 is 3, we're going to get 1, 3, 3, 1. When n is 4, my first number I come to besides 1 is 4. I get 1, 4, 6, 4, 1. And what I'm doing here, again, is I'm adding these two to get that. I'm adding these two to get that 3. I'm adding these two to get the 4, the 6, the 4, the 4 and the 1, the 4 and the 6, the 4 and the 6, the 4 and the 1, etc. Important again that we're starting with n equals 0. Another way to say this is if I find a 5 as my first non-1 coefficient, I know that that means I brought it to the 5th power. If I find a 6 as my first non-1, I brought it to the 6th power. If you were asked to expand a plus b to the 5th, one way to do it would be to use Pascal's triangle and the pattern of the exponents. 1, remember that's n to the 0. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Here is n equals 5. n equals 0, 1, 2, 3, 4, 5. When our n is 5, we're going to have coefficients of 1, 5, 10, 10, 5, 1. 1, 5, 10, 10, 5, 1. Now I know my exponent here is 5, so the addition of these two exponents on the a and b has to equal 5. Start a high, a5, a4, a3, a2, a1, a0. Then start b low, goes to b0, b1, b2, b3, b4, b5. And then just add pluses in between them, and we've just expanded a plus b to the 5th. Note that you don't have to put b to the 0, because we know that that is 1, and we know that a to the 0 is also 1. So actually this would be the answer here.